This is an introduction to the FIRST robotics competition control system. First, this entire unit is built up to demonstrate the components here. This item right here is the National Instruments Robo Rio. It's an ARM9 Cortex processor, memory, and other things in it. It has multiple communication interfaces, including the USB A port, a couple of USB B ports, and Ethernet. It also has, let's see here, SPI port, I2C, and RS-232. We will not be focusing on the SPI or IC2 or RS-232 ports. We will be working with the other ports. On this side here are 10 PWM ports is what they're called. There's an electrical engineering standard for PWM signals. This type of PWM signal is a little different. This is the hobby RC type. It's commonly used to operate model airplanes, boats, and cars and such, servos. This servo here is compatible with these signals. For many years, there have been speed controllers made or motor controllers made that have control circuitry that's compatible with the hobby RC PWM signals. Plugs into here. This item right here is a motor controller. It's the Victor SP. It only does PWM. This model here is obsolete, but still in common use. There are other more modern replacements to that. Across the bottom here, we have analog inputs for measuring voltages for various sensors. There's also a set of digital relay outputs. Here we have 10 digital pins that can be used for input or output, commonly used for encoders or limit switches. RSL is for the signal light. This is the signal light that comes in the kit of parts. It's made by Allen Bradley. If you're not familiar with it, this is the way you wire it up. You're going to take the black wire, and go to the middle pin, take the red and jumper it to both sides. And on the other end is a 2-pin header that's commonly seen in many electronic devices. I'll just plug that in right there. Where do you get this cable from? Well, you can make it in the kit of parts. You'll get a cable that looks like this. It's just a 2-pin header on each end. You can cut it in half, use one half for the signal light. The other half you can use for some other use or just stow away. Another thing that we're going to be doing in our programming exercises is hooking up various devices to the analog inputs. One exercise is we'll just take a PWM cable like that comes in the kit of parts or from a hobby RC store. You'll plug it in here, black to the ground signal right here, which is the triangle. The white wire will go to the top, which is signal. The middle wire we're not going to use, we'll just cut it out. And in one exercise, we're going to use it as create a voltmeter to measure a voltage to make sure our circuit's working correctly. So you can just grab your mouse and pull the battery out. And after you plug this into the analog port, you'll take the black, connect it to the bottom of the battery, and the white, connect it to the top. If you can see like this, and that will be our exercise there. There's another exercise where we'll take the ultrasonic sensor and we're going to use the analog voltage output. Again, the same cable plugs into one of these ports. The power and ground get connected to pins 6 and 7 on this particular sensor. We're going to be getting the analog output, which is connected to pin 3, and the white wire goes there. Just to continue this tour, we're going to go this way. You can see these PWM lines connected to 4 speed controllers. And again, this is the older model. And what we do is we bring the outputs to a terminal strip, and then we can hook another cable to the power strip and plug in a motor, or you can take a motor or some other device and come straight into the terminal strip and bypass this. This is an Anderson power pole connector. The shells are common, but there's at least 3 different types of pins that goes in the inside. And the pin that you use varies depending upon the wire size. One very nice way to dress up these wires before you use them is to use what are called crimp-on ferrules. These are crimp-on ferrules. We got these from Automation Direct. There's a very nice crimp tool that you'd want to get to use that. The Anderson power pole connectors that I showed you a minute ago are available from several sources. Common source for high school robotics teams is Andy Mark. As we come around, our light just went somewhere. As we come around, we feed these speed controllers off of this power distribution board. Ideally, what comes into here is a perfect or pretty good 12 volts. What the speed controller does, it takes a signal from the computer and converts the solid 12 volts to an output voltage that varies anywhere from -12 to +12 volts, which is full speed backwards to full speed forward for your motors. This power distribution panel has more than just circuit breakers. It has some smart electronics in it. It also has the termination for the CAN bus. The CAN bus is the communications bus. There are many communication buses in this world. I2C, SPI, Ethernet. CAN is another one. We'll talk more about the CAN in a minute. You have to pay attention to how you hook up the CAN bus. It's a serial bus. It has a built-in 120 ohm termination on each end. Follow the instructions in the build guide and make sure you wire it correctly, and you can turn the termination on and off somewhere around here. There are some status lights to tell you what's going on. There are 8 slots for 40 amp fuses. The remaining slots, you can use fuses anywhere from 3 to 30 amps. These fuses are automotive type fuses. They're available from many sources, but commonly we get them from suppliers such as Andy Mark and Vexpro. Down at the bottom, there's a built-in voltage, DC to DC voltage converter. It supplies power to the voltage regulator modules, the pneumatic control modules, and creates power for the computer. Come back around here again. This is the pneumatic control module. We need to review this. You can see the green and yellow wire coming around, starting here, coming into the PCM and out of and continue on down the bus. There are 8 controls for operating solenoids for pneumatic controls. There's also a switch for to detect the pressure in the control system for the air system, and another output to drive the compressor on and off. In our exercises, we will not actually be hooking up a pneumatic solenoids to the system. We will just simply look at the lights and see if they're going on and off according to the computer commands that we're running. We'll also connect a switch up to emulate the pressure switch so we can cycle in software the compressor on and off. So if we come on around here, also these outputs here are protected with a pair of fuses there. You should always keep spare fuses with you in case you goof something up. Come around to the other side. Again, we have more DC power feeding the H-bridge motor controllers or speed controllers. On the other side, you saw the Victor SPs, which are PWM control only. These are the Victor SPX. They can handle PWM signals. It can also handle the controller automation network, the CAN signals. It has other intelligence where you can start lashing some control modes together. This is the Talon SRX, which is a more sophisticated model of what's going on here. You'll see a connector shield here. You can pull this off. You can plug in other electronics such as a limit switch or encoders. One nice thing about using limit switches here is you don't have to do any programming. You can put encoders into here, which will change the way you'll program the robot. Also, on this front panel here with the digital I/O pins we talked about, you can hook up limit switches and encoders here. You can hook up limit switches and encoders here. We're going to start out this way and eventually get to this method here. So you'll know both ways to do it. This is a dedicated voltage regulator module. We feed it 12 volts from the power distribution board, and it makes various voltages such as 12 volts, 5 volts, and so on. And this is used to drive things like the radio. Like we have the radio plugged into this one here. The reason for having this is that as the robot's going through a competition match, the 12 volt bus can wildly vary. But for the computers, such as the Robo-Rio and the radio, they need to have very, very stable voltages or they might crash. Again, you'll see on this side, we have 2 cables set up with Anderson power pole connectors, so we can conveniently plug in a motor for testing or evaluation. I want to slide this power supply up a little bit. Well, before I do that, I want to hook this signal light back up. Black goes down to the ground. The ground is the little triangle at the bottom. And this light is very bright and annoying if it's in your face, so I'm just going to drop it in this hole. And we'll hook up a little bit of power, and I can power this thing up so you can see what it looks like. Now it is powered up. You can see the lights are coming on here with various statuses. When you come around here, you'll see some flashing lights. Don't want to drop that. Flashing lights from these controllers. There are no lights on controllers on this side because I haven't put any fuses in. You can see status lights on the voltage regulator module. This is a benchtop power supply. Normally you'd hook up a robot battery to run the machine, but I use this just for benchtop software development and testing. This is the radio. You program it following the instructions from your kit. We have a couple of stickers on here to tell us some things we'd like to know internally. One more quick look at the back again. You can see some status lights regarding communications. Also note that these 2 wires coming into here are not the size wires that you'd use on a robot. This is much smaller because we're not pulling much power on this particular chassis. We've got it fused down. Something to know is that when you put in the real cables here, it's a number 6 cable, number 6 AWG wire. The 2 screws here and the 2 inside under the shell are metric screws. When you take them off, and this piece of plastic, have someone hold them in their hand, mount the cable on, put the screws back on, put the cover back on. You don't want to lose the screws, otherwise you're going to have to do some mail order to get replacements. I think that's a pretty good quick look at the control system. This is a nice convenient little box. We use it for dropping into various test chassis early in our competition season. This internally at Cal Robotics, we call this our flux capacitor. It's what makes robot travel possible.